Section 9.3. Today we are going to take a look at some applications in probability. As fun as you thought that those tree diagrams were, we're going to do some more of them today. I know. We're also going to look at another application, that's where we're going to start, of one of the places that you commonly see probabilities used, but with a little bit different spin. And that language is called odds. So let's talk through what it actually is and then see if you can think of some places where we see it used right now. So if we've got the probability of an event being P of A, then the probability of the A with the bar on the top means it's not an A. The probability that A does not occur. Then if you want to talk about the odds in favor of an event A, then it's the probability of A divided by the probability of A complement. Or you can say it's the probability of A divided by 1 minus the probability of A. And you actually have also odds against an event happening. The phrasing is just a little different, so you have to be a little bit careful. And all it is it's the reciprocal of those fractions that you did on the first bulleted point. Okay, so where do you see or have you seen odds used? Okay. Oh, well, that's unfortunate. Okay. It might be. It really wouldn't be quite as catchy, would it? No, yeah, so probably not going to change it. Oh, some of you know things. You just want to talk out loud. Gambling. Thank you so much. Appreciate it. Gambling. Does anybody know specific gambling events that use odds commonly? Some do and some don't.
Would the lottery be?
You will see it with the lottery. I have a really good example of a lottery one later on. Yep. Horse races is the one that you see it used like all the time. Everybody talks about the odds running horse races. Yeah. Okay, so it wasn't that long ago that everybody, when I asked this question, would talk about Hunger Games, which doesn't exactly fit with the description either, by the way, but that's one people would talk about. But yeah, gambling's the biggest one. And we've actually seen an example of odds. We didn't call it that earlier on. Do you remember back on the first exam, you had a question where I asked you a ratio of boys to girls, and then I had a ratio of boys to the whole class, something like that. And I had you give a description next to it, said part to whole or part to part. Remember that? Okay, probability is a part to whole description. The likelihood of winning compared to the likelihood of anything happening. That's probability. It's a part to whole ratio. Odds is a part to part ratio. The likelihood of winning compared to the likelihood of losing. That's really what odds are. What are my chances of winning compared to my chances of losing? So we're going to do an example that has marbles because gambling would not be appropriate. From a set of 8 marbles, 5 red, 3 white. You choose one at random. Part A says, what's the probability you choose red? Okay, so this is what we've already been doing all the way along. So we say that there are how many red marbles? 5. And how many marbles total? 8. So there's a 5 out of 8 chance, right? 5 marbles out of 8 total that we will pull out a red. The odds that we choose a red is a comparison, again, but this time not compared to the whole. It's a part-to-part comparison. It's my 5 reds compared to the non-reds. So how many of these marbles are not red? 3. So it's a 5 to 3. Now you have to be a little bit careful when you're doing odds simply because sometimes things reduce to whole numbers. Like what if this had said 6 over 3? And then you decide, oh, that's equal to the number 2, and then all of a sudden now there's no like ratio present and it's weird and feeling. You have to have it written in a ratio form. Even if it reduced into something that would be a whole number, you write it over 1, okay? We do want to reduce these, just like we would with probability. So if we have the ability to reduce an odds question down, right? Like if it said, I don't have a good example now. Let's say it said 5 over 10. we would actually reduce it to 1 over 2, right? Okay, so we would still reduce those. So let's take a look at another place where we see people describing things in terms of this language. Probability of rain. Do your phones do that? Chances of rain? Yeah, the weather apps do that. Mine does anyway. So if it tells you that the probability of rain for the day is 60%, what are the odds? And you see this word against, that's really important. Odds against it raining. So let's actually write down a couple of details to remind ourselves. This is actually saying there's 60% chance it rains. And what's the percent chance that it doesn't? Right, 40% chance of no rain. Okay. So when we're looking for odds of something happening, like odds for an event, we want the event that we want to occur to be on the numerator and the event that we're not wanting to occur on the denominator. But it flips it upside down when it's odds against. The odds against the event happening means the event's not going to happen on top. So on this problem, what's going to go in the numerator? The 40. And it really is okay if you write 40% on top, because we're going to reduce all this down anyway in a minute. And you have your 60% on bottom. Okay, it's odds. The likelihood it doesn't rain compared to the likelihood that it does rain. And then we're going to reduce. So what would 40 divided by 60 reduce to? 2 over 3. So there's a 2 to 3 odds that it will not rain. Right? So what does that mean? Well, it means for every 5 days that this were the probability, you would expect that 2 days it would not rain and 3 days it would. Right? That's what this is telling you. The comparison of when it would versus would not happen. All right, so there's obviously a relationship between probability and odds. The odds in favor, if the odds in favor of an event are m to n, then the probability of the event is m over m plus n. And if the odds against an event E are m to n, then the probability is n over m plus n. So we're going to go back to our marble question to see this played out. Has everybody finished writing it? Okay. So over here, what we really saw happening was that there was a 5 over 5 plus 3 probability, right? Right? So when we have this is the likelihood that it happens compared to the likelihood it doesn't plus the likelihood it does. They're added together in the denominator. So that's the relationship that's being described in that sort of formula form on that theorem. So let's take an example then. We've seen this three-child family, I think, before, or at least a version of it. I think we saw a 2-child family, but it works the same way. It says to consider a 3-child family. You've got space on this page, and then the next questions on the next page say, what are the odds of having all the same gender children? And then the odds against having all the same gender children. So we can actually draw a tree diagram. So we've got a boy and girl on the first option, right? Then we have a second child. And it's either a boy or a girl. And it's a 3-child family. So we have a third option. Not option, a third set of branches. All boy girls. Now we did, it's even still behind me on the board, a tree diagram much similar to this with heads and tails, right? We talked about the fact that everywhere along those branches, all the branch options had 1/2 probabilities because they were all equally likely. The same is true for this one. So these all say 1/2 on them. Okay, everybody good with that? All right, so the considerations that we're looking at are the odds of having all one gender compared to differing genders, either two of one and one of the other, or something like that. So there are two branches that have all of one gender, the one along the top and the one along the bottom, right? Two branches. How many branches have a combination of genders then? There's two that had the same gender, all the same genders, right? This one and this one. How many are here in the middle? There's 6. And all these outcomes are equally likely. So there's a couple different ways that we could do this problem because they're all equally likely. Let me show you the hard way, but it works for all options, even if these probabilities didn't match. And then I'll show you the easy way that works because they do all happen to match. All right, so because they all happen to, or because this would work for any option, how many ways are there of getting all of the same children? Well, there's 2 branches, and each one of those branches has a 1/8 probability. Everybody agree with that? Wow. 1/8 probability. So there is a 2/8 probability of having all the same gender of children, compared to what's the probability of not having the same gender of children? 6/8. Fraction inside of a fraction, so we can flip. So this is 2/8 times 6/8. I'm sorry, 8/6. And what happens? Of course, the 8's cancel out, right? This will leave you with, 2 out of 6, or 1/3. Okay, so the odds of having the same gender of children, odds, not probability, the odds of having all the same gender of children is 1/3, 1 to 3. Okay, so this is the hard way because I did it with probabilities, but it works even if they haven't had all the same probabilities. Because these have all the same probabilities, the reality is that there's an easier way that we could do it, is that we could count what is the number of ways of getting all the same, instead of probability, the number, compared to the number of ways of having different genders, some of each. Well, there's 2 ways of getting all the same, and there's 6 ways of getting one of each. So of course the answer works out the same, otherwise it wouldn't be an acceptably different way of doing it. But the reason it works is because all the branches were exactly 1/2, 1/2, 1/2. They all matched. The cool thing is, once you've done part A, you should be able to do part B like this. Because if odds in favor is 1 to 3, then odds against should be 3 to 1. It's just the reciprocal. So you don't need any work to do that. You just need to flip it. And don't tell me the answer's 3, because that doesn't make any sense with context, right? It's 3 to 1. It is a 3 to 1 odds. Okay, there's one more application of probability that we're going to look at. It's a very fun one. Before we do that, are we good, do we feel like, with odds? Okay. Are you okay, Elizabeth? Okay. All right. The other application in this section that we're going to look at is called expected value. Expected value, in a nutshell, is what we expect to happen as a result of playing a game. These are all going to look at outcomes with numerical possibilities. Okay, so I can't talk about the expected value of a gender of a child. That doesn't make sense because it doesn't have a numerical outcome. So we're looking more at like the probability of game theory, right? Like gambling games and games with, horse races, stuff like that. If the possible outcomes of an experiment are A1, A2, all the way up to AN, each with probabilities P1, P2, up to Pn, then the expected value is A1 times P1 plus A2 times P2, all the way up to AN times PN. And hopefully, because you see all the multiplication and addition, you realize, obviously, yes, got to be talking numbers. Can't be talking about boys and girls, right? Doesn't make sense. Did you guys ever tell your parents that's not fair? You're lying if you say you didn't. I know you did. My kids like to talk about fairness all the time. And fair is one of those words that has sort of lots of connotations. What does it mean to be fair? Does it mean we both are equally likely to do something? Does it mean that you have the same chance that I do? Does it mean that you should be able to do anything that you want? That's what my kids think it means. It's not fair if they can't do whatever they want. Well, in mathematics, a fair game means that it's equally likely. And the way that we calculate whether something's equally likely is we calculate the expected value being 0. So if you think about somebody doing like a carnival game, right? So like if you went to the state fair and you threw the darts at the balloons and so forth, right? Or you went to the carnival game and the little weight guesser guy, I don't know why you'd want him to guess your weight, but if you did, what is the expected value of that happening? The reality is, if the expected value is 0, if it's a fair game, it's not at the state fair. It's not. Because if it's a fair game, they'd make no money. Okay? The game cannot be fair. It doesn't mean you can't win. It just means that you're not likely to win, because otherwise they wouldn't have played the game, because they got to pay the guy. Right? And they got to pay, like if you think about in terms of like a casino or something, they've got to pay to keep the lights on, and they've got to pay for the air conditioning. Like there's got to be a way for them to make more money than you do as the consumer. So when we're looking at a fair game, that's what we're talking about. So we're going to talk about in a roulette wheel. If you've seen a roulette wheel, that's great. If you haven't, hopefully this is a descriptive enough problem to help you see what we're talking about. On a roulette wheel, it's just a wheel like Wheel of Fortune, okay? On a roulette wheel, there are slots. They're numbered 0, 0, 0, and then 1 through 36. So how many slots are there? 38. There's 38 of them. One way to bet, there's lots of ways to bet on a roulette wheel, but one of the ways to bet on a roulette wheel is to bet on a single number. You go up and you say, I'm going to put all my money on 0, 0, or whatever. If that happens and the ball lands on your number, then you receive 35 chips back plus the chip you played on the number. Okay, so you bet 1, you get back 36, but you didn't really get back 36. You got back an additional 35 plus the one you lost, right? All right, everybody with me on that? Okay. A says, what is the probability that you will land on 0, 0, or that will land on 0? Okay, so this isn't expected value just yet. We're getting there. What is the probability that you get 0 when you roll? I don't mean 0 as in nothing, but the number 0 when you spin the roulette wheel. 1 out of 38. Yeah, there's 38 options. So what's the probability that you land on 0, 0? 1 out of 38. So if you wanted to know what's the probability that you land on 0 or 0, 0, like if that's how you played the game, it would be 2 out of 38, and you could reduce it. Okay, so this is actually real life. I'm about to show you something real life. I think I just had that twice. All right. When my father-in-law passes a roulette wheel, he's a very bright man, but not when he does this. If he sees that it has not landed on 0, 0 or 0 in recent history, he will bet on both numbers. He really will. He'll go up and he'll put a chip on 0 and he'll put a chip on 0, 0. Everybody with me? Okay. If he bets one chip on each number and a chip is worth $10, we'll get to the $10 amount later, what is the expected value of his bet? Okay, so the reality is he's going to win or lose. There are no other options in this case. He either wins money because it lands on the 0 or the 0, 0, or he loses money because it doesn't. Some of the other games that we're going to see have different outcomes. Like maybe if it rain, like these wheels are colored. So maybe if it lands on these certain colors, you win $1. On these other colors, you win $2, and on this third color, you win nothing. So some of the games we play will have more options. But on this one, he either wins or he loses. Everybody good so far? Okay. So what's really happening for expected value is that we have the probability that he wins times the money amount that he wins. Okay? And we add to that the probability that he loses times the money amount that he loses. So if we had multiple ways of winning different amounts of money, I'd have multiple options here, not just 2. But in this game, we either win or we lose. The lose one is actually the easier one to calculate. So let's actually look at that one first, the second half. He's bet 2 chips. He's bet them on the numbers 0, 0, and 0, right? Okay, so he's got sort of double stakes in the game. I get that. But we talked about on the last problem what the probability was that it landed on, sorry, I've got an extra slide in here. The probability that lands on 0, the probability that lands on 0, 0. And I didn't write it, but I did talk about the probability that lands on 0 or 0, 0 being, and you guys told me it was 2 out of 38. Everybody with me? So if there's a 2 out of 38 chance that he wins, what's the chance that he loses? 36 out of 38. So 36 out of 38, and then I can write in the other one, the probability he wins is 2 out of 38. Okay, now it matters that we're talking about one chip and how much the chip is worth. Okay, so let's talk about him losing. If he loses, how many chips does he lose? 2, because he bet 2 chips. One on the number 0 and one on the number 0, 0, right? And each chip is worth $10. So how much money does he lose if he loses? $20. So this is a negative amount. The question is sort of like, what's the difference in his wallet? Well, it's $20. He's $20 down. This is why I don't gamble, because I could go to dinner on that. Right? Like, really? Okay. How about the value that you win? That's a little trickier, which is why I wanted to do it last. Okay, so it says in the problem, if he wins, where was it? We'll go back to this slide, it's fine. He gets 35 chips plus the chip that he bet for the winning chip. Okay, so he's going to win 35 chips. I agree. But does he really have 35 more chips than he had before the game was started? Right. He spent 2 chips. He's going to get back 35 plus the winning chip. So he spent 2, and he's going to get back 36. So how many chips is he actually sort of like gaining? 34. All right, did we do that right? It's 34. So over here, the value he wins is 34 chips, but each chip is worth $10. So he actually has $340. Is everybody good so far? I think that's the trickiest part, because this is really like the roulette process, okay? So the way that they give you back your chips. Makes you feel like you won more than you did. You didn't win 35, you won 34, right? Okay, that kind of thing on this one. All right, so we have calculators, right? Grab your calculator. We need to know what is 2 over 38 times 340 plus 36 over 38 times negative 20. And it'll be a dollar amount, so whatever we end up with, we need to make sure we do it in terms of dollars and cents at the end, even if there's really, like, you know, more decimals and stuff like that doesn't work for the problem. And you may end up with a negative. You do end up with a negative, actually, yeah. Okay, what did you get? Did everybody get that? Yeah? Okay, so what does that mean? I mean, obviously, if you play the game, you didn't really lose $1.05. That's not what it means. Alicia, do you have an idea?
Like if you kept losing over time, like you would lose $1.05 every time.
Right. This is an average. That's what an expected value is. It's an average. Over time, on average, you're going to lose $1.05 per game you play. Okay? But you got to know it has to work that way, because if it didn't, the casino wouldn't have the game. Right? Remember, they got to pay the guy running the wheel and the lights and the electricity and all that good stuff. Okay, let's talk about the next one. I don't know how far we're going to get into it. Obviously, we're not going to finish this lesson, so no homework over the weekend. I know you're so sad. Contain your disappointment. All right, have you guys seen this show, Deal or No Deal? Yes? Yeah, they always say no deal, and they slam the thing shut, and yeah, all the good stuff. I know. And you're like, dude, you really should. Did you know that there's a version of Deal or No Deal when you go on a cruise ship? We watched it when we went a couple of years ago. It's actually a lot, or actually this summer, my husband and I did. It's actually a lot of fun. We just watched. We didn't play because that would be too stressful. This would stress me out. All right, so here's the way it works in case you haven't seen it. In the television case Deal or No Deal, a contestant is down to 2 cases with equal probabilities of being chosen. The cases have $250,000 in it and $10 in it. The banker, he comes on and he or she, whatever, you can't see them. They offer a deal, right? So you're going to put yourself sort of in the place of the banker and figure out what sort of the idea is behind, behind making that deal. So the cases have, these are options. If you're the banker and want to give a reasonable offer to the contestant but not too lucrative, what deal would you offer and why? So we're going to make our decision based upon expected values. So there are 2 outcomes that could happen for the contestant, right? And they're equally likely, which means what's the probability of each outcome? 1/2. So there's a 1/2 chance that they get $10. And there's a 1/2 chance that they get $250,000, right? So real quick, the math on this, I don't even care if you write it in there, just so you know, it's $125,005. Okay, that's the expected value. So the reality is, as the banker, you'd be offering something around that dollar amount. Slightly more if you're enticing them to try to actually, bail out of the game, right? And slightly less if you're wanting them to play because you think they're going to lose. But it's got to be around that. So you're going to offer around $125,000. Because it's the average value between the 2. If the contestant doesn't take your offer, they're going to win one of those options. So we're looking for sort of like the midway point. Okay? All right, we will finish 9.3 next time.